Okay, let's learn some more about second derivatives, and I'll even throw in a little more about first derivatives into this particular lesson. Number one, the graph of f double prime of x is shown. So you're looking at the graph of the second derivative. Identify all x values at which f of x has an inflection point. When you first look at this, you might think, okay, to find the inflection point, I find the second derivative and set the second derivative equal to 0. And that would lead you to conclude that this blue point is where the second derivative equals 0, and this one, and this one, and you would say, this is a pretty easy question. X equals -2, x equals 1, and x equals 3. However, I have given you this scenario to think about because I want you to have to review the fact that the inflection point is where the concavity changes from positive to negative or negative to positive. Now, considering that, if we look at the second derivative graph again, right here, the second derivative is positive, so the original function is concave up. And then right here, the second derivative is positive, so the original function is concave up here. So the original function is concave up, and then no concavity for a moment, and then concave up again. So right here, the concavity of the function does not change. If you look at this part of the graph, the second derivative changes from positive to negative, so the function is concave up and then concave down. That makes this an inflection point. At x equals 3, the second derivative changes from negative to positive, so the original function changes from concave down to concave up. So the concavity changes. So this is also an inflection point. So if we're looking at our values, -2 has to be crossed out. It's only x equals 1 and x equals 3 that are inflection points of the original function. Number 2, given the second derivative shown, identify all x values at which g of x has an inflection point. So in this time, I'm giving you an equation for the second derivative. And in the first scenario, I gave you a graph. To do the second scenario, it would help to be able to picture the graph of this function. To picture it, we need to look at the overall degree of this function. So look at this x. That's x to the first power. X minus 3 would be x minus 3 to the first power. X plus 2 is to the second power. You don't have to multiply all these terms together to realize that g prime of x, or g double prime of x, is going to be -5x to the fourth power, and then ... Since we know the second derivative is a fourth degree polynomial, let's sketch a graph of it, because that will help us determine where the inflection points are. To start sketching a graph of the second derivative, let's start by finding the x-intercepts of the second derivative. So imagine setting the second derivative equal to 0, and then solving that equation. There are 3 factors in this factored form that it's in, and I'm not going to show the work for that. I'm assuming you know how to do this part. But x could equal 0, or 3, or -2. Those would be the x-intercepts. Let me mark those on my function. So the graph of the second derivative has to pass through those 2 points, or those 3 points. If we think about the behavior of this second derivative, it's going to be a fourth degree, and its end behavior is going to be below the x-axis on the left and the right side. And so that means it's going to be coming up toward this x-intercept. Now, if you'll notice, the x-intercept of -2 comes from this factor of x plus 2 squared. Since the factor is squared, the function is going to bounce as it hits that x-intercept and then come back down again. When it gets the x-intercept of 0, it's going to pass through. And when it gets the x-intercept of 3, it's going to pass through because those factors have odd exponents. Now that we can see the shape of the second derivative's graph, it becomes a lot easier to determine the inflection points. The inflection points are where the second derivative changes from positive to negative. It would change from positive to negative when x is 3, and it will change when x is 0, but not at x equals -2. Moving on to number 3. Draw a section of a curve that has the following characteristics: concave upward and decreasing. Concave upward means it's something like this. Decreasing means something like this. So we need to make a curve that is going downward and also concave upward. So it might look like that. That would be an exponential curve would look like that. You could make it look maybe part of a sine curve. You just need to draw a single section of it. I don't care how much you draw. Just want you to think about the fact that that's what it would look like if it was decreasing and also concave upward. Part B, f of x is less than 0. So that means it has negative y values. So there's my x-axis. It's going to be underneath that. And then f double prime of x is less than 0. So that means it has a negative concavity or concave down. So it needs to be below the x-axis and concave down. If you drew an upside down parabola, that would be a common example of something that has negative y values and is concave down. Number 4. If you are moving in a car and you have a positive velocity and a negative acceleration, how would you describe the motion of the car at that moment? Well, positive velocity means the car is moving to the right in a positive direction. Negative acceleration, I'll put the positive velocity in blue. Negative acceleration means something's pushing back and slowing the car down. So the car is moving to the right and slowing down. Now I realize when I say moving to the right, I'm assuming that moving to the right means that's the positive direction. But what maybe your positive direction would be defined differently. Number 5. Suppose you are moving up and down on a carnival ride. If you have a negative velocity and a positive acceleration, how would you describe your motion at that moment? So a negative velocity means your speed is going downward. A positive acceleration means the acceleration is pushing upward. So you're going down, but your velocity is decreasing. In number 6, I'm giving you a graph of the derivative, and I want you to decide where the original function has its greatest y value in this interval. At what x value does the graph of f of x have the greatest y value? To do this, you have to remember that the second derivative tells you the slope of the original function. In this region, the derivative is showing that the original function is increasing. Then the original function is decreasing, still decreasing, then it's increasing and decreasing again. This increasing part and this decreasing part match up and basically cancel each other out. So all of the increasing movement is canceled out by this decreasing movement because the slope here is positive 40, the slope here is negative 40, and everything in between here matches up there. In this region, the graph decreases more than this increase right here. So there's more decrease than this increase. And then there's increase here, but decrease there, so these cancel each other out. If we pull all that together, the graph of the original function increases and then decreases, continues to decrease, then increases and then starts decreasing. This collective portion of decreasing is greater than this collective portion of increasing. Let's look for a moment at the points where the derivative is 0. Right here, right here, right here. When the derivative changes from positive to negative, that represents a relative max in the original function. When the derivative changes from negative to positive, there's a relative minimum. And then at x equals 6, there would also be a relative max because the slope changes from positive to negative. So our question really is, which of these two relative maximum points, this one or this one, are higher? This one ends up being the higher relative maximum, the greater y value, because the graph increases heading into that and then decreases by the same amount, but continues to decrease more than it increases right here. So this collective amount of decreasing is less than this amount of increasing. And you'll eventually learn that if you think about this right triangle and this triangle, the area of this right triangle is greater than the area of this triangle. So the amount of decrease here is larger than the amount of increase here. So this relative maximum does not come up as high as this relative maximum. I think it's very likely that you find some of that still to be confusing, and I'm okay with that. I think being challenged at this point is actually still beneficial for you in terms of stretching your learning. But I have scenario 7 here designed to continue to think about this in a way that is tied to something that you can maybe picture or imagine more. Look at the function in the previous scenario again. Now imagine that the graph shows your velocity as you move up and down on a carnival ride. The x-axis shows time measured in minutes. The y-axis shows your velocity. A positive velocity means you are moving up, away from the ground. A negative velocity means you are moving down. Assume that you start far enough above the ground when x equals 0 that you never touch the ground during the ride. Estimate how many seconds into the ride you reach your greatest height above the ground. Well, we already know that that occurs when x equals 1. And x is measured in minutes at this point. So x equals 1 would be 1 minute or 60 seconds. But the reason for that can be thought of or discovered using what you know about speed. This derivative is showing you your speed, your velocity, I guess, if we're thinking about direction of the speed. This is a positive velocity. 40 is the velocity, and then down to 0, and then negative 40 is the velocity. So these two parts cancel each other out again. And this part is a decrease, starting with a decrease with a velocity of negative 40, negative 30, negative 20, negative 10, 0, and then we have an increase. Now, does this increase cancel out this decrease here? Well, this increase goes from 0 to 20 and then back down to 0 again. The maximum velocity here is 20, whereas the maximum velocity in this region is 40. This is a 2-minute section of time. This is a 2-minute section of time. The maximum velocity in this goes from 0 up to 20 and then down to 0 again. This has a maximum velocity of 40, which is why this decrease exceeds that amount of increase. And again, why this is the point at which, or the time at which, you are highest above the ground. In number 8, given the derivative below, identify all x values at which f of x has a critical point. In this scenario, I'm trying to get you to remember that critical points occur when the derivative is equal to 0, and also when the derivative is undefined. I'm going to show when the derivative is equal to 0 in black and undefined in red. Since the derivative is a fraction, it will be equal to 0 when the top expression is equal to 0. And since it's a fraction, it will be undefined when the denominator is equal to 0. I made the top expression look as it does because I want you to review factoring by grouping. Factoring by grouping is where you essentially split it up into two groups and look at the common factors in each group. So the first group, the left group, has a common factor of x squared, and the resulting factor when you factor out an x squared would be x minus 2. And the second group, we could factor out a negative 9, leaving x minus 2 as the remaining factor. And these two groups have a common factor of x minus 2, which leaves x squared minus 9 when we factor out an x minus 2 from both of those two groups. And then I put this one to give you an expression that can be factored even more. X squared minus 9 is x plus 3, x minus 3. From all of this, we see that there are values where this expression equals 0 when x equals 2, and negative 3, and positive 3. Now let's look at the denominator expression. I've set that equal to 0. And I wrote this expression because I wanted you to realize that you can factor out a common factor. Sometimes we forget that as an option for factoring. When I set these two factors equal to 0, if x squared is equal to 0, then x can be 0. If x plus 4 is equal to 0, then x could equal negative 4. Putting this all together, we have 5 critical points.